Hello, this is Brother Kumar from the Math Department, and this is a continuation of Lesson 9, Inference for When Means Sigma Known, Hypothesis Testing. And so we already talked about the difference between a null hypothesis and an alternative hypothesis. And we talked about a type 1 and type 2 errors. Those are the two errors the two possible errors you can commit when you do do a test hypothesis. But now we're going to talk about a how-to for a hypothesis test, testing one mean where sigma is known. Okay, so let's talk about this a little bit. When the observed results are unlikely, assuming the null hypothesis or H naught is true, the result is what's called statistically significant. And if statistically significant, we reject the null hypothesis. So for instance, if a sample mean has too many standard deviations from the mean stated in the null hypothesis, we reject the null hypothesis, and that would be an example of an unusual value or a rare event. So say, for instance, on this normal distribution curve, at the center is the null hypothesis. If we get a sample mean that's out here, x bar out here, or perhaps out here, that would be an example of an unusual value relative to the null, and therefore we reject the null hypothesis. Okay? So, assuming the null hypothesis is true, if the probability of getting a sample mean is extreme or more extreme than the one obtained is very small, we would therefore reject the null hypothesis. That would be area under a normal curve, which is what you've seen before, but now we're going to do it in the context of a hypothesis test. So how do we do this? So by definition, the p-value is the probability of obtaining a sample mean. We'll talk about what a test statistic is in a sec. Or a test statistic is least extreme as the one you calculated, assuming the null hypothesis is true. And we'll go through an example of this, a visual in terms of what that means. So the p-value is compared to the level of significance. What's the level of significance also equal to? Well, the level of significance, or alpha, is also equal to the probability of committing a type 1 error. So if we get a p-value less than the probability of committing a type 1 error, then we're going to reject the null hypothesis. So if the p-value is smaller than alpha, this would be considered a rare event, and the null hypothesis would be rejected. One more note here, the guidelines must be set prior to the analysis, meaning we need to set our level of significance ahead of time before we do our analysis and compare a p-value to the level of significance. Okay, so if a p-value is smaller than alpha, this would be considered a rare event and the null hypothesis would be rejected. Here are examples of rare events or unusual events. If we're doing a right-sided test or a right-tailed test, if we get a result, a sample mean that's out here, that would be considered a rare event. If we do a left-sided or left-tailed test, if we get a sample mean out here, that would be considered a rare event. And if we're doing a two-tailed test, if we get it on either side here, on the answer in the brown area here, then that would also be considered a rare event. Okay. So now what I'd like to do is let's talk about briefly the requirements for doing a one sample standard deviation unknown. The sample has to be from a simple random sample. The population standard deviation needs to be known, and either one of these conditions are satisfied. Either the original population or the parent population is normally distributed, or the sample size n is greater than 30. That's the guideline, but basically the sample size is large. This goes back to the fact that we have to deal with the central limit theorem. We have to have our distribution of sample means be normal. Either the original population is normal, or we have a large sample size because of the central limit theorem. Okay. So now what I'd like to do is talk about the 5 steps for doing a hypothesis test. Step 1 is state the null and alternative hypotheses. We talked about that in the last video. Step number 2 is to compute the test statistic. Here's the test statistic. It's the z-score. I referred to this earlier with the p-value here, where we say the probability of obtaining a sample mean or test statistic is least as extreme as the one you calculated, assume the null is true. So the step 2 over here is the test statistic. It's the z-score. You've seen this formula or something similar to that before back in Unit 1. Then step 3 is get the p-value, and so we'll use the applet to get the p-value. And then step 4 and step 5 is what you're going to be seeing throughout the semester. Step 4 is that we would all ignore this, the decision rule, because we don't have that as a definition. But we reject the null hypothesis if the p-value is less than the level of significance. If not, then we don't reject. And then we state our conclusions. If we reject the null, we have sufficient evidence to say that, and then we state the alternative hypothesis in English. If we don't reject the null, then we have insufficient evidence. We state the alternative in English. So I'll go through a couple of completed examples here in the next slides here. So let's get to it. Here's the first example. So when people smoke, the nicotine they absorb is converted to cotinine, which can be measured. Historically, the mean cotinine level of all smokers is equal to 200 micrograms per gram. You would like to see if it has decreased. A simple random sample of 40 smokers has a mean cotinine level of 160 micrograms per gram. Assuming the population standard deviation is known to be 119.5, use a level of significance of alpha equal to 0.05. So step one is state the null and alternative hypothesis. So the null is that the population mean is equal to 200 because we got that information of historically that the mean cotinine level is 200 micrograms per gram. You'd like to see if it's decreased, so the alternative hypothesis is that the mean is less than 200. Step number two is we calculate a z-score. So we take this formula here, x bar minus the null, this represents the null hypothesis, divided by the standard deviation over the square root of n. So we take the sample mean we got, which is 160, minus the null hypothesis, which is 200, divided by our standard deviation, which is 119.5, the population standard deviation, and we divide that by the square root of 40. And then we solve for all this, and we get a negative 2.117. Now, does that look like a rare and unusual event or value? Well, if you remember our definitions back in lesson 5, anything below, a z-score being below -2 or above 2 would be an unusual value or an extreme value. So this would be an extreme value. But how we confirm that is where we get our p-value. So what we do is we go to our applet and we type in negative 2.117. Okay, we press enter. And then the question is, where do we shade? Well, since we're doing a one-sided test on the left side, we shade to the left, which we already have. And so now we get a p-value of 0.017. This represents our p-value. So going back to the definition of a p-value, this is important. This will be one of the main emphasis for this course. The probability of obtaining a sample mean or test statistic is least as extreme as the one you calculated, assuming the null hypothesis is true. So this is the test statistic that was calculated, or more extreme, so it says at least as extreme as the one you calculated. That's what this shaded area represents. This symbolizes the definition of a p-value, this shaded area right here, okay? And this is an important definition you'll need to know throughout the course. So going back to the problem here, our p-value is 0.017, and that's less than our level of significance, so therefore we reject the null. And since we reject the null, we have sufficient evidence to say that the mean cotinine has decreased from 200 micrograms per gram. So now what I want you to do is that I want you to stop the video and I want you to go through this example by yourself. Okay, so based on historic data obtained from Brother Birch from the grade point GPA, or the GPA of students at BYU, Idaho, is known to have a mean of 3.15 and a population standard deviation of 0.68. Okay, we want to determine if the mean GPA is now different. So skipping the sentence, a total of n equal to 30 people were surveyed and asked to report their GPA from last semester. The mean of the GPAs in the sample was computed to be 3.263. Use alpha equal to 0.05 level of significance to test the claim. So the mean is equal to the null hypothesis, mu is equal to 3.15. The alternative, we want to see if it's different. It's now the mean, the population mean is not equal to 3.15. To calculate using this formula to get the test statistic, we get a test statistic of 0.91. Now, right here, we can say, is this a rare and unusual value? Well, since it's not above 2 or less than -2, it doesn't look to be. But we can confirm it by going to get a p-value. Now, the p-value I got was 0.3628. But what we can do is that if I shade both sides, since this is a two-sided test, type in 0.91, press enter, and then I get my p-value of 0.3628. So, since our p-value is 0.3628, do we reject the null hypothesis? Well, in this case, we do not, since our p-value is greater than alpha, so we don't reject the null. And then, in this case, we have insufficient evidence to say that the mean GPA is different than 3.15. So in our conclusions, we always refer to the alternative hypothesis, and if we reject the null, we have sufficient evidence, but since we didn't reject the null, we have insufficient evidence for the alternative hypothesis. And that concludes the lesson 9 videos dealing with inference for one mean, sigma unknown, primarily dealing with hypothesis testing. If you have questions, please speak to your instructor or to your TAs.